Hi, how's it going, guys? My name's Andy Nguyen, and I'm here to talk about ATP and its pathways of synthesis within our body. To start off, we have ATP, or adenosine triphosphate, which is an energy-rich compound that is made up of adenosine, ribose, and three phosphate groups. The cool thing about ATP is that it can extract potential energy from foods and save it within its bonds, and it can also transfer that energy to perform biological work in our body, i.e., like digestion, muscle action, circulation, nerve transmission. ATP must be resynthesized at the same rate of its expenditure to meet energy demands. So the body stores very little ATP at a given time. It can store up to about 80 to 100 grams. And synthesis ATP synthesis relies heavily on ATP concentration, as it's very great, or very the body wants to maintain balance through homeostasis, and any change in the concentration between ATP and ADP is going to set off it's going to stimulate the breakdown of other compounds that can produce ATP. So here we're going to start off with glycolysis and the Krebs cycle. We start off with glucose, and that is going to break down right here through a bunch of reactions and turn into two pyruvates. These reactions over here produce two ATPs and two NADHs. I'll get back to NADH later, as I'll talk about it in another process. So now we have pyruvate. It's going to have to enter a preparatory phase, I would say, to turn into acetyl-CoA before going to the Krebs cycle as well. Pyruvate must oxidize into NADH, or oxidize into acetyl-CoA, releasing NADH and carbon dioxide. Then the acetyl-CoA can go through the Krebs cycle, or the citric acid cycle, in which the acetyl-CoA is going to combine with oxaloacetate and through a series of reactions, it's gonna build and break all throughout, and it's gonna generate certain products like 2-carbon dioxides. It's gonna generate some NADHs, FADH2s, ATP. So, but because there's two pyruvates, this reaction occurs twice, as shown here. So we get our numbers. We get 3 here, 3 plus 3, 6, 7, 8, 9, 10. 1, 2 right here for FADH2, and then 1, 2, 3, 4 for ATP. Now we go to the next cycle, or the next process, which is the electron transport chain. This is the last part of the glucose breakdown into ATP. This transport chain essentially just transports the NADH and FADH2, the ions from here, the H ions, through the inner mitochondrial membrane, through cytochromes, these structures, into the outside the membrane, or into like the intermembrane space. Now, when these reactions occur, or not reactions, but the transportation of these ions or electrons occur, it's going to release some energy, and every time it does, it's going to go down. Just there's lower energy being released, but the energy is creating a higher concentration up here, which will force these ions or electrons to come back down into this area due to diffusion, as when they want to go high to low concentrations. And it's going to do that with the help of this structure right here, ATP synthase. And that's going to, as ions or electrons are funneling through the synthase, it's going to spin. That structure is going to spin and force ADP to combine with phosphate to create more ATP as well. So this on top of this yields about 38 ATP for one glucose molecule. Then we can talk about fatty acids, or in this case specifically, it's going to be palmitic acid, just because that is the most common source, or most common fatty acid in our body, therefore making it a very plentiful source of energy. We're going to start off with the fatty acid, and it has to go through a process called beta oxidation. So beta oxidation is literally the breakdown of a fatty acid into acetyl-CoA, and this happens about 7 times, just because palmitic acid does have 16 carbons, and each cycle of beta oxidation is going to remove 2 of those carbons. So we have to complete this cycle about 7 times just to get the full breakdown and use all of it for ATP synthesis. So we start off with acetyl-CoA, and it's going to go down, and then it's funny because I thought this is very reminiscent of the Krebs cycle, in which something's being broken down and forming FAD or FADH2 and NADH, and as well as acetyl-CoA, because they use these products as well to form form more ATP. So I thought that was pretty cool. It made me understand it a little bit easier. So first we have to break down acetyl-CoA, and once it's breaking down all the way, it'll create an extra one, because you can't really break it down again. So it's going to leave us with 8 acetyl-CoA. And then during each cycle of this, 1 FADH2 and 1 NADH are going to be formed, and also 1 ATP is going to be formed. So that's going to leave us with 8 total acetyl-CoAs, 7 NADHs, and 7 FADH2s. Also 8 ATPs. I'm sorry. So then these numbers will be coming from, so since we have 8, I took 8 here, and then in the citric acid cycle, it's going to produce, 1 acetyl-CoA is going to produce 3 FADHs. So I did that, I took that and multiplied it, and then I added another 7 from the ones we already get from beta oxidation. Same thing here, I just did, you get 1 FADH from the process of Krebs, or the Krebs cycle. So you do times 8 cycles, and then you get it, and then you have to multiply it by 2. Sorry, you have to multiply by this by 3, because it's 3 moles per NADH of ATP per NADH, and this one is 2 moles of ATP per FADH2. And then you add this 8 from the ones being generated here, subtracted by 2 for the input, and then it leaves you with 129. So we can see that palmitic acid does, or fatty acid breakdown produces more than glycolysis. So what factors limit these pathways? Glycolysis is regulated by metabolites and cellular concentration of ADP. So metabolites are things that can activate or inhibit enzymes to in key points in the oxidative pathways, and they modulate the speed, or they moderate the speed and the of the reaction between glycolysis and the Krebs cycle. As for cellular concentration of ADP, that's, like I said before in the beginning, that it serves as a cellular feedback mechanism to maintain the balance and between ATP and ADP. And at rest, the concentration of ATP to ADP is 500 to 1. As for beta oxidation, though, beta oxidation relies heavily on the breakdown, or the glycolysis breakdowns, because that produces oxaloacetate, which is a key component in the beta oxidation. Pyruvate also helps determine levels of oxaloacetate, as if we have low pyruvate, we're going to have low oxaloacetate to use. So intermediates from carbohydrate breakdown are very important to beta oxidation's process, and it can only occur with these intermediates from the carbohydrate breakdown. So there's a saying in the book, the textbook, that says fat burns in a carbohydrate flame. So that makes a lot of sense. Fat only, it's also important to note that fat breakdown only provides half of the power when compared to carbohydrate breakdown. So that means that muscle aerobic power must decrease if we have a decrease in our glycogen stores, just because that's one of the first things we're going to use. And because of that, we have to rely on other sources, i.e. glycolysis, to provide us energy. So what happens when our body goes through intense conditions or different exercise conditions? Our body's going to rely heavily both on fats and carbs. It is a balance. At first, we're going to start with fats or glycogen stores in low intensity and low duration. So like when you're just starting. And then as time duration it picks up, we're going to start going into our fats from our adipose. And then past around 5 minutes, we're going to start going into our carbs, just because we're going to have more of those readily available than we do from our glycogen and fats. So also the concentrations of these things will change and decrease over time due to increased demands. So ATP and ADP and NADH and NAD are going to fluctuate throughout not fluctuate, but just gradually decrease as intensity increases. So how do we tie it together? I think it's important to note that fatty acid relies on carbs, or fatty acid breakdown relies on carb breakdown because of the oxaloacetate component. And our body we have to utilize both for optimal performance. So we don't run out the storage of either system. Beta oxidation also provides significantly more ATP than glycolysis, as we saw, 128 to 38. But in terms of what we're going to use glycogen and fat first before we use our glucose stores. And because we know this information, we could use it to our advantage in physical training, as we can tailor certain exercises to maximize these energy systems, developing both an aerobic and a anaerobic metabolic capacity to perform optimally. So that's my presentation. I hope you guys learned something. Here's my references, and I had a lot of fun learning about this stuff. So I'll see you guys next time. Thank you.